This is the second video in my little mini unit on absolute values. So in this video, I'm going to go over how to use absolute values when you're drawing graphs, when we're dealing with absolute value functions. So going straight into things, an absolute value function, and this should not be surprising to you if you've looked at all at radical functions or rational functions or anything like that. An absolute value function is just a function with an absolute value in it. But specifically a variable inside that absolute value. So let's start with the easiest one we can, which is just going to be y equals the absolute value of x. So to kick things off, this isn't an absolutely necessary mandatory step, but it is going to make our lives much easier as we go. We're going to actually ignore the absolute value, and we're going to start by graphing just y equals x. So this isn't going to take up a ton of space, so I'm just going to sketch myself a little 3x3 grid down here, and we'll talk about that as we go. So it might have been a little while for you since you've graphed any linear equations. I'll do a really quick review right now, but if you're feeling a little bit lost, feel free to take a look at the Pre-Calculus 10 videos on my channel that cover graphing. That would be chapter 5, assuming those videos are there. If you can't find them, do let me know. But quick review. Remember, the basic linear equation is y equals mx plus b, where m is your slope. And remember, slope is just rise over run. And then b is your y-intercept, so where you cross the y-axis. So for our particular equation here, y equals x, our m is just 1, or 1 over 1 if it makes your life easier, and our b is 0. So we're going to start with our y-intercept at 0, and then our slope is just 1 over 1, so we go over 1 and up 1, over 1, up 1, and we do that until we get enough points. So we've got points there, and then we can go in the other direction and do the same thing. And so this is y equals x. But we didn't want y equals x, right? We wanted y equals the absolute value of x. So how does that change things? What does that absolute value do? So we're going to compare the graph that we have now and see if we can use it to get that absolute value version. So let's make ourselves a couple of table of values. First, for y equals x without the absolute value. So we had x and y, and we've got some points. So -2, -1, 0, 1, and 2. And so if you plug those x values in, well, y equals x, so you're just going to get the same thing, right? Right, so if x is 0, y is 0, if x is 2, y is 2, and so on and so on. If we do y equals the absolute value of x, though, let's see what changes. We're going to use the same x values, right, because we're using the same little graph. So -2, -1, 0, 1, and 2. And so if you plug -2 in there, well, if we've got y equals the absolute value of -2, that's going to be +2. So when x is -2, y is +2. When x is -1, y is +1. When x is 0, we get 0. And then for those bottom two, when x is 1, y just stays as 1, because remember the absolute value of a positive doesn't change. And same for 2. And so we end up with those. And so you'll notice, hopefully, that the x values are still the exact same. Those haven't changed. What has changed is some of our y values. And this happens in a really predictable and controllable way. So all that ends up happening is to graph an absolute value if you look at your y values, the only ones that changed were the ones with negative y values. So this -2 and this -1 are now +2 and +1. So what we do is we flip any point with a negative y value to be a positive y value. Keep in mind, though, that this is a very basic way of doing this. This only really works when the entire function is contained inside the absolute value. So in Pre-Calc 12, you're going to see cases where you might have the absolute value with a coefficient on the outside with a +3 at the end. That is going to change things, but for us, this year, Pre-Calc 11, all we do is we flip negative y values to positive y values and move on with our lives. So coming back up to our graph, if we're doing y equals the absolute value of x, we got -2, 2, we got -1, 1, 0, 0, 1, 1, 2, 2. And so if you look at the graph and you compare them, you'll see that part of the graph hasn't changed. So these points are all exactly where they were. Right? So this graph is the same graph. And then part of the graph has flipped from being negative to positive, just like we said. So this part hasn't changed, and then this part has moved up to be up here. And so that's all you really need to do. If you know how to graph the original function, just take all your negative y values, flip them up, and then you're done. And so if you look at this absolute value function, which is just the blue part, let's get rid of the red part just to hide things for a sec. This is y equals the absolute value of x. This is what we were originally looking at. And so you can kind of look at that graph and see that it sort of has two pieces. It's two straight lines. And so we're going to have to do something with those two pieces to kind of describe what this graph is covering. So we've got two parts, one part that flipped and one part that didn't. And we're going to have to express that in a way that's understandable to somebody who's looking at just the equation without even being able to see the graph. So those two pieces together are going to form sort of a combined equation. So the right half of our graph, this part that wasn't flipped, is still just y equals x, because that's what it was originally, right? We graphed that, it didn't change. It's just y equals x. So the right half, in this case, is the original, just y equals x without the absolute value. The other half, the left half in this case, did flip. And so if you look at that just as a linear equation, you ignore everything else. Let's erase a bunch of stuff to clear this up. If I just asked you for the equation of this line that you see here, well, it's got a y-intercept of 0 still, but now its slope, instead of being +1, is now -1. So let's go down here and we'll fill that in. So our left half of the graph is now y equals -x. And so our goal is to write some kind of function that puts these two things together. And so that thing, that equation that combines them, has a name. They form what we call a piecewise function, right? Piece because it has two pieces. And a piecewise function is just a function that's made up of a few different pieces, right? So it's a function that's made up of two or more pieces, and those pieces are typically separated based off of the range, based off of the x values. So looking at the graph we have here, sorry, if I said range earlier, I meant domain, right? So based off of our x values. So looking at what we have here, we've got a pretty clear split right in the middle, right along the y-axis. It's not always going to be along the axis. We'll see several examples coming up soon that aren't. So the way we're going to write this, we've got our original absolute value function, y equals x, can be written as the following. So it's y equals, and then we're going to have just one curly bracket. We're not going to close this, so just a curly bracket on the left. Half of it is x, and half of it is negative x, right? So that's what we figured out right here. And then we just need to describe the x values for those two pieces. So the top part, positive x, is when we're on the right of the y-axis. The second part, negative x, is when we're on the left of the y-axis. And so the dividing x value there is just 0. So it's y equals x when we have x values that are greater than or equal to 0, right? Positive x values. And it's negative x when it's not that, when it's less than 0. And so this is a piecewise function. So we're going to want to write these for our absolute value functions after we graph them. So let's try another one. We'll go through the whole process, and it'll hopefully make a little bit more sense once you see it sort of in one smooth piece. So we're going to graph y equals the absolute value of 2x minus 3. All right, so ignoring the absolute value, the 2x minus 3 has a slope of 2 over 1, or just 2, and a y-intercept of negative 3. So sketch yourself a 5 by 5 grid, right? 5 up, 5 down, 5 left, 5 right, and then come back and we'll try graphing this thing. Okay, so our y-intercept again was at negative 3, and then our slope is 2 over 1. So from that negative 3, we're going to go up 2 and right 1, which gets me a point here, and then up 2 and right 1, up 2, right 1, and so on and so on. And remember, you can always go the opposite as well. So instead of going up and right, we can go down and left, which gets me a point down here at that point there. I'm going to put a line through my points. You don't have to, because we're not actually interested in this part of the equation. We're just using this as sort of a guide. So you could certainly skip putting the line through the points at this stage, but just to kind of help explain things, I'm going to go ahead and get that line up there. So that's y equals 2x minus 3 without the absolute value. So now, to do y equals the absolute value of 2x minus 3, we're going to flip any point that has a negative y value. So these 3 points up here, these aren't moving because they all have positive y values. But these 3 points down here, those are all going to flip because they all have negative y values. So the x value doesn't change. So this point here has an x value of 1 and a y value of negative 1. So now it's going to be at 1, positive 1. Then our y-intercept, which is currently 0, negative 3, is now going to be 0, positive 3. And then that negative 1, negative 5 is now going to be negative 1, positive 5. So all of these points here haven't moved. And all of these points down here have flipped to become a new line going up and left. The sort of inflection point, the place where these lines have flipped, is this point right here at our x-intercept, right? So that's where we go from being negative y values to positive y values. So those x-intercepts are going to be pretty important to us here. So now, if we're graphing our absolute value function, the left part of that is going to look something like this, right? So this is the part that's flipped. And the right part is just going to line up with the piece that's already there, which is that. Do make sure that you graph both of those clearly so that you show that you're graphing both the flipped part and the unflipped part. And again, you don't have to have the line for the original thing, so you could absolutely just have this. You could even maybe skip those points at the bottom, although it's definitely helpful to graph them. But this is a pretty standard way of showing this. Now we just need that piecewise function. So we've got 2 parts, and it's always going to be kind of the same thing. So the first part is the bit that we didn't change, 2x minus 3. The second bit is the part that we did change. And so if you look at that blue line on the left, so this bit over here, the slope of that is now negative 2 instead of positive 2. And the y-intercept is now positive 3 instead of negative 3. So the second half of your piecewise function, this bit here, is always just going to be the opposite of the original function. And when I say opposite, I just mean opposite signs. So all you basically do is just multiply everything by negative 1. And now we just need to talk about our domain and our range here. So for the first bit, we want the x values that are to the right of our x-intercept, which was at, well, we don't have a clear point, but that is going to be at 1.5. So we want all the x values that are greater than or equal to 1.5. And that's the part that didn't change. The second half that did flip was when x was less than 1.5. It's not always going to necessarily be the same greater than or less than. It depends on which part ends up flipping, but it is always going to look something like this. You can't have the equals in both of these. So we typically include the equal part in the bit that didn't flip. The part that did flip doesn't get the equals. Because otherwise you're saying that one part is in both, and we can't really do that. All right, so I'm going to give you one of these to do on your own, and then we're going to try it out with parabolas afterwards and see how that changes things. So we've got y equals the absolute value of negative 2 over 3 x minus 2. So I would say sketch yourself a 6 by 6 grid just to make sure you have enough space. And then get this on there, do the absolute value, and try to do the piecewise function. So put it all together, see what you come up with, and then come back and see how you did. All right, so for our original unflipped, unabsolute valued function, we have a y-intercept at negative 2, and then a slope of negative 2 over 3. So we're going to go down 2, right 3, down 2, right 3. So remember, negative slopes versus positive slopes are super important to watch out for. And then instead of going down and right, we can also go up and left. You definitely need to make sure you have points both above and below your axis when you're doing this so you can see what does flip and what doesn't flip. All right, so I'm not going to draw the line this time. I'm just going to look at the points I've got. So these points on the left, these two aren't going to change. They're going to stay where they are. But these 3 points down below, so this one, and this one, those aren't part of my absolute value. Those are all going to get flipped up above the axis. So that 0, negative 2 is now 0, positive 2. Then we've got 3, positive 4, and 6, positive 6. And then these 2 points over here have stayed where they are. So now I end up with this. So if we draw our lines just for our absolute value graph, our function looks like so. Kind of like a check mark. And now we just need our piecewise function. So we've got y equals curly bracket, so the original function, and then the opposite of that. So the other version is just going to be, and I might need to slightly bigger curly bracket here, so positive 2 over 3x plus 2, which you can see with this positive slope over here and this y-intercept at positive 2. The inflection point where we change is at our x-intercept, which is down here at negative 3. So regardless of which one I'm looking at, both of these things are going to be based off x being around negative 3. It's just a question of whether we want to be bigger than that or smaller than that. So the unflipped portion is over here on the left. This part hasn't flipped, and that is when x is less than negative 3. So our original unflipped equation is x is less than or equal to negative 3. The flipped equation is x is greater than negative 3. And so there we are. That's graphing absolute values for linear functions. But what if it's a parabola? It doesn't really change the thought process too much. It's just basically going to be working with parabolas instead of working with linear equations. So let's try graphing y equals the absolute value of x minus 3 squared minus 4. So sketch yourself out a 6 by 6 graph for this one as well. And then once you're done, we'll come back and we'll talk about how to graph this thing. All right, so we are graphing a parabola here. So if you need a refresher on that, I'll do a really quick summary, but make sure you go back and check out the 3.1 videos on graphing in vertex form just to get yourself up to speed. So remember, our vertex is at positive 3, negative 4. So we're going to get a point down there at 3, -4. And then we've got our pattern of 1, 1, 2, 4, and 3, 9. We don't have an a value here, so that pattern's not going to change. So we're going to go from those points over 1, up 1, over 2, up 4, and over 3, up 9. And remember, you need to have some points above and below the axis to really make this work. All right, so if we draw ourselves our parabola, again, you don't really have to draw this one because we are going to end up flipping some of it, and some of it is not relevant to the graph that we actually want for this equation. But since it's our first one, it's not a bad idea just to get it out there so that we can visualize what's going on. All right, and so our process for graphing our absolute value hasn't changed. Again, all of the points with positive y values or 0 y values, so those 4 points there, those are all going to stay exactly where they are. Any point with a negative y value, which is these 3 down here, those are all going to flip. And really, remember, it's this entire thing that's flipping. So I'm highlighting the specific points with clear values, but every point flips. So my vertex is going to go from -3, or +3, -4 to +3, +4. Then those next 2 points are going to be there and there. And this whole bit in here is basically just going to be a parabola, but now facing down instead of facing up. And so we're going to end up with a piece that looks like this. The outside bits, you can think of like the wings of our parabola, aren't going to flip. So these 2 pieces out here are going to stay exactly where they were because they had positive y values. And so our absolute value function, we can just kind of trace those, and we're going to end up with something that looks like this, which looks really messy. So if I erase the bottom real quick, there's our absolute value. It looks kind of like a person holding their hands up, maybe. And so that's what a parabola looks like. Hasn't made a huge difference in the process. It's just you have to graph a parabola instead of graphing a line. It is going to make the piecewise function slightly more difficult. So let's get that going. We've got y equals, and then so we have the original x minus 3 squared minus 4. And then we've got the flipped version of that. So keeping in mind, the x values haven't changed, which means my p value for my vertex is still at +3. So the number inside the brackets, that's not going to change. It's just the stuff outside of the brackets. So it's going to become negative because this thing is pointing down now. X minus 3 squared, and now it's going to be +4 instead of -4. So that's the equation for sort of this inside flipped part of our parabola. Then we got to talk about x values. So the original unflipped part happens on the outside part of our graph. So that's over here and over here. So you'll notice how that has 2 pieces. And so we actually have to write 2 separate domains to cover that bit. So we have one part that happens if our dividing values are at 1 and 5. The left unflipped part of the graph happens when x is smaller than 1, right? So it's everything on the left. The right unflipped part happens when x is bigger than 5. It's the right part of the graph. So that's me describing the ranges for this part over here and this part over here. The middle part is in between those 2 things, right? It's in between 1 and 5. So that's going to happen. And if you don't remember how to write a domain when you're in between 2 values, it always looks pretty much the same. It happens when x is bigger than 1, but smaller than 5. And so for parabolas, our absolute value piecewise functions are often going to look something like this. With that being the case, we're going to try one last one, and then we'll wrap this up with just a couple quick discussion points. So I'm going to get you to graph this one without me. So you're going to graph y equals the absolute value of -2 x plus 1 squared plus 3. So a 5x5 graph will do. So get that sketched out, draw your graph, try to do your piecewise function. You're going to hit a bit of a snag on the piecewise function, and we will talk about that. So give it your best shot, and then come back once you're done. Okay, so we've got points at, well, we've got our vertex, rather, at -1, +3. And so remember, with your pattern, your 1, 1, 2, 4, and so on and so on, if you have an a value like we do here, those vertical distances get multiplied by that a value, so by -2 in this case. And so you'd be going over 1 and down 2, and over 2 and down 8. So from that vertex, let's go over 1, down 2 on both sides, over 2, down 8 on both sides. Gets me these 5 points. In this case, we actually do have to draw the original unflipped parabola, because we're going to need it to figure something out in a bit. So let's make sure we draw that now, and then we'll come back and talk about something later. Let's make sure we draw it maybe a little bit better than that, though. So as you were doing your original thing, you might have noticed that something was a little bit tricky here. And so remember, when we're figuring out our piecewise function, a key component of that is knowing where our x-intercepts are so we can talk about our domains. But on this one, we don't have clean x-intercepts. When we were working in chapter 3 and chapter 4, we would have maybe just estimated where those are, but for this, we're going to need specific values. So how do we find those x-intercepts? Well, if we go back to chapter 4, remember the x-intercepts are basically the same thing as the solutions. So to figure out where those are, we're going to take that original unflipped, unabsolute valued function of -2 x plus 1 squared plus 3, and we're going to set it equal to 0. And then we're just going to solve this. We're going to do this not by factoring, not with the quadratic formula, because this is already in vertex form. So we're just going to isolate x. We're going to do some opposite operations here. So let's subtract 3 on both sides. It gets me -2 x plus 1 squared equals -3. Divide by -2 on both sides, which gets me x plus 1 squared equals 3 over 2, or I'm going to go with 1.5 because decimals are going to be okay here. We're going to square root both sides, which gets me x plus 1 equals plus or minus, don't forget that, 1.22. Then I'm going to subtract 1 on both sides, which is going to get me x is -1 plus or minus 1.22. So my two x-intercepts are x equals -2.22 and x equals positive 0.22. And so all of that was just to tell me where my x-intercepts are, just so I can write a better piecewise function. So it's a lot of work. All right, so we haven't even done the absolute value yet. Let's go back and look at our graph. So remember, to do absolute value, we're going to flip these negative y values to be positive y values. So that those are both going to go up to +5. And so our absolute value function, once we graph it, is going to have these three same points here. It's going to have these same x-intercepts at -2.22 and positive 0.22. And it's just going to look something like this. And these get a little bit annoying to graph because there's a lot going on, but just do your best. So there we go. That's not the best. Maybe let's make that a little better. And so if we get rid of the original one, we'd have something like this, which gets the point across. It's not beautiful, but it shows the absolute value. So all that's left to us is to do our piecewise function. And so we're going to need some space for this. So let's go all the way down here. We've got y equals, and so the original function was -2 times x plus 1 squared plus 3. The flipped version of that is going to have an a value of +2. Remember, the p value doesn't change. It's still at x plus 1. And then it's going to be -3. So those are our two functions. And so now we just need to talk about the domain for these. So it's going to use these x values over here. That's why we bothered finding them. So the original unflipped part is the bit in the middle this time. So this part is unflipped. That part stayed the same. So that part of the piecewise function happens when we're in between those two x values. So when we're in between negative 2.22 and positive 0.22. The flipped part happens when you're outside of those values. So that's the part on the right and on the left. So when you're smaller than negative 2.22 or bigger than 0.22. So that's x is less than negative 2.22 or x is greater than 0.22. One thing to consider, parabolas don't always have to have positive values and they don't always have to have negative values. So if you had a parabola that looked like this and you did the absolute value, it would just stay exactly the same. If you had a parabola that looked like this and you did the absolute value, the whole thing would flip and you'd get something up top like that. So do consider when you're doing it that it does depend on where your parabola is located. And so there we are. Those are absolute value functions. So our last video for this chapter is going to go over how to solve equations that have absolute values in them. And it's going to rely on some similar stuff to what we did in this video, but with a little bit more. So once you're ready, go take a look at that.